All right, let's begin. So this is the 2014 multiple choice test. Okay, some of the more complicated ones, maybe I will go through and work from scratch, but otherwise I may just work from the key and explain every step. But feel free to jump in at any time, ask me a question through meeting chat or just unmute your mic and let me know if you have a question. Okay, so number one, we want to take the definite integral from 2 to x of 3t squared minus 1. It looks a little bit different here with that upper bound not being a constant, but we go through the same process. Okay, looks like there's nothing that is hindering us from applying power rule. So we're going to do power rule first, and then the bounds come last, right? We never want to involve the bounds until after we've done our calculus antiderivative step. Okay, so we go through power rule first. All right, so power rule 3t squared becomes 3t cubed over 3. 1 dt becomes 1t, and we do a little bit of cleanup, and we're left with t cubed minus 1t, and then we can work in our upper and lower bound. Upper bound is x. X gets inserted in for t. We get x cubed minus 1x minus parentheses. Then we work in the lower bounds. Okay, so it's good thing to remember that anytime we're doing upper minus lower bound, if there are multiple terms, that the lower bound is going to have to be protected with a set of parentheses so that we don't forget about the negative that has to distribute through the parentheses. Okay, so lower bound, 2 inserts for t, 2 cubed minus 1 times 2. And now we're just trying to clean this up here. So x cubed minus x minus 8 plus 2. And the constants combine to be negative 6. All right, number 2. What is the slope of the line tangent to the graph of y equals natural log of 2x at the point where x equals 4? So it's as simple as finding the derivative and then evaluating the derivative at that point. So with our function, we just do u prime over u, since that's the rule for natural log. So natural log of u is u prime over u. So to find the derivative, 2x becomes 2. The denominator is our 2x. So there's our derivative is 1 over x. And then insert 4 into the derivative, and we get 1/4. Now, keep in mind, this section is non-calculator. So even though some of these things can be plugged into the calculator, we want to make sure that we are working these problems appropriately. Okay. And only using them or only using a calculator when needed. Sorry, only use a calculator for the second section. Okay, number 3. Guys, give me 1 second, all right? 1 second, I'll be right back. Okay, so number 3, our function is 4x to negative 2 plus 1/4 x squared plus 4. Find f prime of 2. So this is also pretty straightforward. Every term is set up nicely for power rule. So we just go through power rule and then evaluate the derivative at 2. So 4x to negative 2 becomes negative 8x to the negative 3. Right? Just go through power rule, bring down the exponent and subtract 1 from the exponent. 1/4 x squared becomes 1/4 times 2x, and the 4 goes to a 0. Okay, do a little bit of cleanup here. Negative 8 over x cubed plus coefficients reduced to be just 1/2 x. And then once we have our derivative, we can then insert 2 in for our derivative. Okay, so 2 in for x. We get negative 8 over 8 plus 1. Negative 1 plus 1 is 0. All right, number 4. Now we're moving on to antiderivative. Antiderivative with bounds, but remember, with any antiderivative problem, we always ignore the bounds, right? We always take care of the calculus first, and then the bounds is the last thing to be applied. All right, so this problem, pretty straightforward. Looks like it's not quite going to be something that we can handle using power rule. So our next option is U-substitution. And looks like our U value is going to be pretty clean, just that entire denominator. Okay, so we let our denominator be our U value, 2x plus 1. And we're just trying to get the 2x plus 1 and the dx in terms of U. And once we get that coefficient lined up, we should be able to recognize a rule that we can use. Okay, so U equals 2x plus 1, du dx equals 2. We solve for dx, we get du over 2. Make our substitutions. And we're left with 1 over U times du over 2. Do a little bit of cleanup here, push the 1/2 out in front, and we can see this is clearly our natural log rule, right? 1 over U du, and integral 1 over U du is just natural log of s value of U. Hold on to that 1/2. Once we have our antiderivative, we're going to bring our original variable back, and then we can work in the bounds, right? What we don't want to do is we don't want to insert the 1 and 2 in for the U because there's a mismatch of variables, right? This is in terms of U, but the 1 and 2 are in terms of X. So we want to make sure that our variables match. Okay, so we bring our original variable back. U gets replaced with 2x plus 1. Okay, so now work in our upper and lower bound. Upper 2. 2 times 2 plus 1, which is 5, minus lower bound, 1/2 natural log, 2 times 1 plus 1. So natural log of 5 minus natural log of 3. 1/2 is the coefficient for both. We can factor a 1/2 out, and that matches our answer choice E. Okay, the figure above shows the graph of the function f. Which of the following statements are true? Okay, first one, limit as x approaches 2 from the left side of 2 is equal to 2. So if we find 2, okay, and we're approaching 2 from the left side of 2, if we're approaching 2 from the left side of 2, that's, and negative 1 is the same thing, the order pair f of 2, so those are in agreement. Okay. Limit as x approaches 6 from the left is limit as x approaches 6 from the right. That means is the graph approaching the same y value from both sides of 6? And here's 6. We pick points on either side of 6. We follow the graph towards 6, and we see the arrows are headed towards the same destination. Even if there's a hole there, we don't really care. We just want the arrows to point to the same location, and it is. And they're both pointing to a y value of negative 1. So we know the limit exists. That is true. Third statement, the limit as x approaches 6, okay, which we know is negative 1, is the same thing as f of 6. Now, this is not true, right? Because the order pair is defined in a different location than where the limit is defined. So these are not equal. So therefore, this is false. The limit does not equal to where the order pair exists. Only the first two statements are true. All right, number 6, sine cubed of x squared. What is the derivative? The thing we have to keep in mind is we understand that anytime we see that shorthand form written, it's always good to use brackets, right? If you put it out as in a set of brackets, we're going to be able to identify the portions a lot cleaner. So I use brackets and I put the 3 outside. Okay, so now we see the 3 different layers that's involved here. You got the bracket cube, that's the outermost layer, and then you have the sine parentheses, that's the second, that's the next tier in, and then finally the innermost portion is x squared. This is a composite function here, function within a function within a function, and we have to take turns with each of their derivatives. Okay, so we start with the bracket cube. Bracket cubes, we do power rules, so 1/3 bracket squared, oh, sorry, 3 bracket squared. Multiplied by sine's derivative. Sine's derivative is cosine. And then finally, the innermost function is x squared, which is 2x. So we're making sure that we're not nesting each of these parts within each other. They are all separate, taking their own separate space. And now we just insert with the originals. Okay, so whatever was inside the original bracket goes here. Whatever is inside the original parentheses inside the sign goes here. 3 sine x squared quantity squared times cosine x squared times 2x. Our answer, we just have to kind of rearrange it to make it look like answer choice E. Drag the 2x to the 3, we get 6x. Sine squared of x squared, cosine x squared. Okay, number 7, limit as x approaches infinity of x cubed over e to the 3x. I'll go through the 2 different methods here. One method is going through comparative growth rates. So if our limit as x approaches infinity, if we have our families of functions in the numerator and denominator being completely unique from each other, then we have this this order of one function always being able to be organized in this order. So logs grows at the slowest rate, followed by radicals, followed by polynomials, and followed by exponential. So you have a polynomial divided by an exponential, or we could say algebraic. Algebraic over exponential. An exponential grows at a faster rate than polynomial. So if your denominator is growing at a faster rate than the numerator, then that means your fraction is getting smaller and smaller and smaller, and so the limit is approaching 0. Okay. We can also do L'Hopital's rule. L'Hopital's rule says if I plug in infinity here, I get infinity over infinity. This is considered indeterminate form. So we could go through our derivative process. X cubed becomes 3x squared. E to the 3x becomes 3e to the 3x. Plug in infinity, we still get infinity over infinity. Find the derivative again. 6x over 9e to the 3x. plug in infinity, we still get 0, infinity over infinity. And then evaluate the limit again, and we get 6 over 27e to the 3x. If I plug infinity in for the denominator, I get 6 over infinity. And I know that is a really, really small number, which is approaching 0. Okay, number 8, using substitution, using letting u equal sine to the 2x. So they're nice to kind of show you what the u value is, so that can help you kind of move you along in the correct starting with the correct steps. So we go through u substitution, we convert integrand and the upper and lower bounds to be in terms of u. But let's not worry about the upper and lower bound first. Let's just try to see where this u substitution takes us. Okay, so I'm going to rewrite it with brackets. So I'm going to push that 5 outside as a set of parentheses. So this feels a little bit cleaner, a little bit more structured. And now I know I'm going to target that u value to be sine of 2x. So that's my starting point. Okay, so I let the u value be sine of 2x. Derivative, sine of u becomes cosine of u times u prime. Cross multiply, we get dx equals du over 2 cosine of 2x. All right, we make our substitutions. This becomes u. Dx gets replaced with du over 2 cosine 2x. And we make our substitutions. Everything hopefully in terms of u. And we see that the dx gives us the 2 cosine 2x in the denominator. We see the cosines cancel out nicely. We can push the 1/2 out in front. And we have 1/2 integral of u to the 5th. So this, we don't have to go any further because it's already matching the form that we see in front of us, right? We know there's a 1/2 in front. We know that E and A are not correct. We just have to figure out what the bounds are going to be. Now, the bounds are not going to be pi over 6 and pi over 2, okay, because we have a different variable here, right? This is a different variable adjusted to be in terms of u. So we have to go through our conversion to get our bounds matched up with the variable that's in play. Okay, so we go through and we convert our bounds. So this is the way we convert. Okay, we use this formula here. This is our conversion formula. U equals sine of 2x. Okay, so if our lower bound starts off as x equals pi over 6, we make that substitution, u equals sine of 2x. So therefore, pi over 6 and for x, 2 times pi over 6 is pi over 3. Sine of pi over 3, okay, so recall your unit circle value is going to be root 3 over 2. Okay, so we go through our conversion with our upper bound as well, pi over 2. Insert that in for x. 2 times pi over 2 is pi, sine of pi is 0. So our lower bound is root 3 over 2, and our upper bound is 0. Now, this is where I feel some students may get a little bit thrown off. You're looking at this and you may be thinking, wait, 0 should be the lower bound because it's a smaller value, and root 3 over 2 should be the upper bound because it's a higher value. But whatever starts as the lower bound is going to remain as the lower bound. Whatever starts in the upper bound is going to remain in the upper bound. Now, if we want to flip the bounds, we have to change the sign. But notice that there's no negative out. Well, there is for this one, but it's not matching with our answer choice here. So there's no negative in front. We have to keep it in the order that is presented. So root 3 over 2 to 0 is going to be the appropriate order. All right, so it's easy to pick answer choice C because it feels more correct to have that lower bound being the smaller value. But if it flip-flops, it doesn't matter. If it starts the lower bound, we're going to have to keep it as lower bound. Okay, any questions there with 8? All right, number 9. Function has a first derivative given by f prime. So it's already at f prime level. At what values of x does f have a relative maximum? So think about first derivative test. We can set f prime equal to 0. It's already in factored form. We can just pull our critical points, which is going to be 0, 3, and -1, right? You set each portion equal to 0 for x, 0, and -1. You can go ahead and plot your sine line. So once you have your sine line, which is -1, 0, and 3, you're going to choose values in each subinterval. So we'll choose -2 because -2 is to the left of -1. We'll choose -1/2 to test. We'll choose 1 to test, and we'll choose 4 to test. Now they all get inserted into the derivative. We're testing it against the derivative function. So if I 2 in, negative times positive times negative, which is positive, 2 negatives. I can basically ignore this middle portion because it's being squared. We know that nothing will ever come out of it except for positive. It's just x and x plus 1 that has a chance of changing sides. Insert -1/2. -1/2 is -1 is negative. -1/2 plus 1 is positive. Negative times positive is negative, so decreasing. Insert 1. 1 is positive. 1 plus 1 is positive. 2 positives makes a positive. Plug in 4. Positive, positive. Okay, so we know there's relative max at -1, to min at 0, and neither at 3. The problem is only asking for relative max, so relative max is at -1. Okay, number 10. Let f be the function defined above for what value b is f continuous. So whenever I see the word continuous and I see a piecewise function, okay, I'm thinking, all right, I try best to just go through continuity conditions. That way I have everything structured and I kind of just follow my way through those conditions. So my continuity condition says, first condition, does the point exist? My point exists for 2. I know the 2 is the center of my problem right now. Does my order pair exist at 2? 2 is defined for the point here. So based off of these conditions here, b value is where the point is. But the graph, the connected parts of graph is really with the first part, right? This x doesn't equal to 2 means that this is the graph that's defined everywhere except 2. This is only a single point that where the graph is defined. Okay? Everywhere else is looking at this curve here. Okay, next up, we want to find the second condition is, does the limit exist? So we want to find limit as x approaches 2. Limit as x approaches 2 for our function above. So first thing we do with limit problem is we insert 2 in for x, and we're going to get 0 over 0. I did not, but if I were to plug in 2, I get 4 minus 14, which is -10 plus 10, which is 0. 2 minus 2 is 0. 0 times b is 0. And because we get 0 over 0, We can either go through L'Hopital's rule or we can factor. I just decided that I was going to factor. It looked easier to just quickly get that numerator factored. So I got the numerator factored. I removed the whole, which is the x minus 2, and I reevaluated my limit. Substituted 2 in for x. 2 minus 5 is -3. -3 over b is my limit. So I continue moving forward. Okay, it's asking for what value of b is the function continuous. So we're trying to get this to work. We're trying to find the b value that will allow all three conditions to work. So now my third condition is, does the point live where the limit lives? So I look at the result of my first two conditions, and I see, is there any way I can set these equal to each other and solve for my missing variable? So I try setting b equal to -3 over b. But when I do that, right, I move the b over, I get b squared equals -3. I try to solve for b, take the square root. I can't do square root of -3, at least in the real number system. This is imaginary number, but in this course, everything is in terms of the real number system. So there's not a real number, and so there's no real value for b. Okay, number 11. Okay, for x between 0 and 6, the graph of f prime, which is right here, it's given. Piecewise linear graph, so made up of lines here. If f of 0 equals 1, what is the maximum value of the graph on this interval? So we're starting at f of 0 equals 1. We know that the area underneath the graph on my f prime graph is going to show me how much distance I travel to the right. And then anything below the x-axis is going to be my displacement to the negative direction. And then here, moving positive again. So also, if I think of this as a derivative graph, anything above represents positive slope. Anything below represents negative slope. So I have positive, slope 0, negative, slope 0, positive. So if I look at my original graph in terms of my slope, I see there's a relative max at 3. There's a relative min at 5.5. So I know there's a relative max at 3. So basically I have to just figure out what is the location of my graph at x equals 3. I like to use this formula. Final position equals initial plus displacement. I'm looking for f of 3. I'm starting at f of 0. So I want to bridge that gap between 0 and 3. So the integral from 0 to 3 of f prime is just the area under this graph. 1/2 base times height, 1/2 3 times 2. So 2's cancel out, I get 3. Insert 3 for my definite integral. 1 plus 3 equals 4. Right, f of 0. Definite integral is 3. So the result of that will be 4. Okay, number 12. Let me work this out by hand here, or from scratch. Let f be the function given by y equals 9 to the x. So this is an exponential function, just to kind of give you a visual here. Exponential function looks like 9 to the x, looks like e to the x. They all kind of have the same shape here. Right. If 4 subintervals of equal length are used, what is the value of the right Riemann sum from 0 to 2? So 4 subintervals, our a is 0, our b is 2, right, lower and upper bound. And then our n value is 4. If I want to create 4 subintervals, I know that my width for my each subinterval is b minus a over n. So b minus a is 2 minus 0 over 4 equals 1/2. Okay, width is 1/2. So I'm going to create my 4 subintervals here. Okay, I want Riemann sum, right Riemann sum. So that means for each subinterval, right? So one subinterval, 2, 3, 4. With each subinterval, I want the right Riemann sum. So I want the right endpoint to connect to the curve, and then letting that be the height of that rectangle. So for my first subinterval, it's going to be the 1/2 that's going to attach itself to the curve. And I'm going to let that represent the height of my rectangle. Second interval, right Riemann sum is going to be with this point. So I'll move until I attach myself to the graph. This is going to be the height of my second rectangle. So, okay. Third rectangle is going to be dictated by 3/2. This will be the height of my third rectangle. My fourth rectangle is going to be dictated by this point at 2. So interval, I'm going to identify the width, which we know is 1/2, and the height. The height is going to be x values attaching it to the curve. So it's going to be the height of my first rectangle. F of 1 will be my second rectangle. The height of my third rectangle will be f of 3/2, and the height of my fourth rectangle is f of 2. So we know the integral from 0 to 2 of f of x dx. Right, it's an approximation. Width times height, right? F of 1/2. 1/2 width times height. Now the function is 9 to the x. So I can insert the 1/2 in for the x. So this is the true height of my first rectangle. Second rectangle, plug 1 in for x. So the height is actually this point here, which is 9 to the first power, which is 9. 9 to the 3/2 will be for my third rectangle. And last rectangle, 9 to the 7. Okay, so 1/2 times root 9 is 3. 9 to the first power is 9. This is the square root of 9. So I can do I know without a calculator, we can just do the square root first, right? The square root of 9 is 3, and 3 to the third power is 27. And then 1/2 times 81. Okay, so 3/2 plus 9/2 plus 27/2 plus 81/2. And this cleans up all the way to 60. All right, 13. All right, 13 is pretty straightforward. This is numerator, denominator. We can just go through quotient rule. Careful, right? We can't just say 1 over 2x like it shows here, right? This is trying to exceed. This will get caught trying to, do a rule that doesn't exist, right? I mean, we could maybe do this if it's a limit problem. We're trying to do L'Hopital's rule, but here we're trying to find the true derivative. So we got to go through the full quotient rule. Okay, so f prime g minus fg prime all over g squared. Distribute, combine like terms, and get it all the way to match answer choice C. All right, next up. A velocity of a particle moving along the x-axis is given by v of t at time t. Particle is at x equals 4 when t equals 0. What is the position of the particle when t equals pi over 2? So I have velocity, I'm looking for a location, and I have a starting point. So this always goes back to this formula I like to use. Let's see, in terms of a particle motion problem, final position equals initial plus displacement. So I want to find x of pi over 2. I know what x of 0 is, and now I just have to figure out what is the displacement between and pi over 2. Okay, we can't plug this in the calculator because this is a part of a non-calculator section. So we have to go through U-substitution. We let our U value be 2t. Go through that process. U equals 2t. du over dt equals 2. Solve for dt, we get du over 2. Make our substitutions. Parentheses gets replaced with u. dt gets replaced with du over 2. Pull the 1/2 out in front. Now we're ready for our antiderivative. Sine becomes negative cosine. Don't forget, bring your original variable back. Bring back the 2t. And now you can work in the bounds. Upper bound is pi over 2. Lower bound is 0. Upper bound first. Insert pi over 2 in for t. Now we don't do cosine of pi over 2 because we got to deal with that 2 in front. So 2 times pi over 2 is actually pi, and cosine of pi is actually -1. Okay, same thing with that 0. 0 in for t. 2 times 0 is 0. Cosine of 0 is 1. So we get 1/2 plus 1/2, which is 1. And then don't forget our initial starting position, x of 0. We start off at 4. We make a progress of +1. So 4 plus 1, we end up with a location of 5. Okay, let me go over 15 here. 15 says the function y equals g of x is differentiable and increasing for all real numbers. Okay, increasing for all real numbers, which means that we know that that g prime is always positive, right? If our function is always increasing, that means our slope is always positive. I'm just going to put this information to the side. We're going to need this later, potentially. On what interval is the function y of g of x cubed minus 6x squared increasing? So this is kind of strange because we can't quite work this out the way we would like because it's stuck inside that function. However, we know that anything that's involved with increasing or decreasing is going to be connected with slope or derivative. So let's go ahead and find the derivative, what we can in this form. So we're going to go through first derivative test first derivative test, but we need to get to our derivative. Now, this is a function within a function here. It's stuck inside that function notation. So we have to kind of go through a little bit of a chain rule. Okay. So if our y is g of x cubed minus 6x, then our y prime, right, we have to apply chain rule. Outside portion is that g parentheses, and the inside portion is that x cubed minus 6x. Okay, so outside's derivative, g parentheses, becomes g prime. Okay, we keep everything intact inside. Multiply by the inside function's derivative. So x cubed minus 6x's derivative is 3x squared minus 6. So we want to set g prime or y prime equal to 0. Oh, sorry, minus 6x squared. I did not put that here. Okay. Then 3x squared minus 12x. Sorry. Accidentally copied it wrong here. Now we know that, okay, it's like, what do you do with this portion? Well, we know that g prime is always positive, so we already know that this portion is positive. We can just basically ignore this portion. It's always going to be a positive number here. Because they say that g prime of anything is greater than 0, so we know this whole g prime is 0. So we can just find our critical values, go through first derivative test simply with that 3x squared minus 12x. I set that equal to 0. So set each portion equals 0, 3x equal to 0, we get x equals 0. Set x minus 4 equal to 0, I get x equals 4. And now my y prime sign line. Okay, we can test the different values here. Test -1, test 1, test 5. Insert into my derivative. -1 in for x, that's negative. -1 in for this x, we get negative. Negative times negative is positive, and this portion is always positive. So 2 positives makes positive. Okay, insert 1. 1 in for x, that's positive. 1 minus 4 is negative. Negative times positive is negative. Right, 5. 3 times 5 is positive. 5 minus 4 is positive. 2 positives makes a positive. So increasing would be both the intervals here, from -infinity to 0, and then from 4 to infinity. Okay. 16, this one feels a little bit tricky because it's like, what do we do with limit with absolute value? Okay, well, anytime we see an absolute value, we can always treat an absolute value as a piecewise function. You can always think of an absolute value as made up of 2 linear graphs, right? Have a starting and starting point and end point for the other. Okay, so let's start off with just the numerator, right? Let's say I had just this y equals absolute value of x minus 3. Okay. All right, now how can I rewrite that as a piecewise function? Well, absolute value of x minus 3 looks like this. It's just a graph that's looks like a V right side up and has a vertex at 3, 0, right? So how can I write this as 2 separate linear functions? Well, it's made up of x minus 3. This is the positive slope version of it. It's going to be living to the right of 3. And then you also have the negative version of it, which is negative parentheses x minus 3. And this graph is living to the left of 3. Now, there's an equal sign here. It doesn't matter where you put it, as long as you put under one or the other. So this piecewise function represents this numerator, right? All right, so let's do this. We know what absolute value of x minus 3 looks like. Or we know what it's defined to be. Again. So absolute value of x minus 3 divided by x minus 3 would then look like this, right? So what if I just divide that x minus 3 to both of my piecewise, because this is really spelled out and defined as both portions, right? One to the right of 3 and one to the left of 3. So I'm just going to take this and transfer it over to the true defined linear version of that x minus 3, absolute value of x minus 3. Now, see what happens here. What does this reduce to be? X minus 3 over x minus 3 is just 1, right? And this negative parentheses x minus 3 over x minus 3 is just negative 1. And if you look at this graph, what does this graph look like? You want a y value of 1 to the right of 3. And then you want a graph that is y equals negative 1 to the left of 3. And if you ask yourself, what is the limit as x approaches 3 from the left side of 3? That means you want to pick a point side of 3 and head towards 3. You can clearly tell that to the left of 3, I'm heading towards a y value of negative 1. So my answer choice is B. All right, number 17. Now 17, this is a is a constant or a leading coefficient. This basically is e to the negative ax. If we want to find the derivative, let's think of that as basically falling to the family of e to the u. We know the derivative for e to the u is just e to the u times u prime. So we find the derivative, we get a, well, we know ae to negative ax. We know a will stay. That's just the coefficient attached to the variable. And then e to the u is just e to the negative ax times negative a, right? Negative a is the derivative of negative ax. And we just try to clean this up here, push the a's together. Negative a squared times e to the negative ax, that matches answer choice E. All right, 18, a student attempted to solve the differential equation dy dx equals xy with initial condition y equals 2 and x equals 0. Which step, if any, does an error appear first? So I like to start off when I do differential equation solving by forcing that second both sides to give me a fraction. So if I don't see a fraction on the right side, I made it xy over 1. Okay, cross multiply. Dy on the left, dx on the right side. So I have my dy dx in their right positions. We just have to figure out what is out of place. And what's out of place is that y. So we divide that y over to the left side. dy over y equals x dx. Both sides have, we now have full separation of variables. Take the antiderivative. This is 1 over y dy, which is natural log, absolute value of u. Integral of x dx is, we go through power rule, x squared over 2 plus c. Okay, so natural log x, absolute value of y, x becomes x squared over 2 plus c. And the way we would go about solving for y, we can raise both sides with e as the base. But when we do that, we know that this plus c is sitting up as the exponent. And if I want to resolve that positive sign in the exponent, I have to separate using multiplication, right? So e to the x squared over 2, not plus e to the c, but times e to the c. So that's where the mistake is showing up. It should be times e to the c. And then once I clean up the left side, the e in natural log goes away. Absolute value of y should equal to e to the x squared over 2 times c, not e to the x squared over 2 plus c. So there's the mistake that's where the mistake is occurring. We can stop there and say that step 3 is where it's wrong. We'd have to go further to solve this, to solve for c and to solve for y. Okay, 19. Right, for what values of x does the graph of y equals 3x to the 5th plus 10x to the 4th have a point of inflection? So here are the steps for points of inflection. We first find f double prime. We find critical points, set f double prime equal to 0. Right, we create our f double prime sign line, and we confirm that the point of inflection has a sign change. Okay. So we go through our steps. Let's make our way to the second derivative. Everything is set up nicely for power rule. So we get 15x to the 4th plus 40x cubed. Keep going through our derivative step. 60x cubed plus 120x squared. Find our critical points. We can set our second derivative equal to 0. $60x squared is our GCF. Factor 60x squared out. We're left with x plus 2. Set the 60x squared equal to 0. Set the x plus 2 equal to 0. We get x equals 0 and x equals -2. Now we have two critical points. Now these are potential points of inflection, but we got to be careful that we don't just stop here and say, okay, I have my critical points and there's my answer. We haven't gone far enough. Okay, if we want to confirm there's a point of inflection, we still have to create a sign line and actually see that there's actually a sign change. All right, so we sign line for concavity. Right. -2 and 0 are our critical points. I can choose values in each subinterval. I'll choose -3, I'll choose -1, I'll choose 1. Insert into my second derivative function, factor form. -3 and for x squared is always positive, so I can just ignore that. The only thing that's going to cause my sign change is this x plus 2. So -3 and for x, -3 plus 2 is negative, so concave down. Insert -1 in for x. -1 plus 2 is positive, so concave up. Insert 1 in for x. 1 plus 2 is positive, which is concave up. So just because we have critical points at -2 and 0 doesn't guarantee that those are points of inflection. And here we see that 0 is not a point of inflection because there has to be a sign change in order for that critical point to earn that point of inflection status. Okay, no sign change, so no point of inflection. Okay, number 20. The first thing I do with the limit problem, I'm just going to go ahead and insert x, 2 in for x, and see what that gets me. So 2 in for x, I get natural log of 5 minus natural log of 5, which is 0. 2 in for x, I get 2 minus 2, which is 0. So 0 over 0 is indeterminate form. And when we get to indeterminate form, we have the flexibility to now apply L'Hopital's rule, which is take the derivative of each numerator and denominator separately. So we'll treat the numerator separate from the denominator. So the derivative for natural log of x plus 3, we know the rule for natural log is u prime over u, so 1 over x plus 3. Natural log of 5 is a constant, goes to 0. X goes to 1, and the 2 goes to 0. Once we have our expression, now we can reevaluate. So 2 gets inserted in for x. 2 plus 3 is 5. We get 1/5. 1/5 matches our answer choice, B. All right, 21. Functions w, x, and y are differentiable with respect to time. So with respect to time, that kind of gives it away that we're dealing with related rates. And we have our equation, which is w equals x squared y. So as a quick reminder of related rates, we find the derivative like we normally would. It's just that every time we find a variable's derivative, we always have to immediately attach a d over dt for that variable. So here we're going to be expecting a dw dt to show up, dx dt, and dy dt to all show up in our derivative process. Okay, every variable is being impacted by time, so we're going to see d over dt's everywhere. Okay, so gathering some information here, x is decreasing at a constant rate of 1 unit per minute. We know that x is decreasing is not just x, it'll be dx dt. There's a rate involved, time component involved with x, so we call it dx dt. And it's decreasing, so we know that value is going to be negative. So I'll put that off to the side. Dx dt equals -1 unit per minute. Y is increasing at a constant rate of 4 units per minute. So y is increasing. We know it's not just y variable, it's dy dt. So dy dt is a +4. Right? At what rate is w changing? So we're looking for rate at which w is changing. We're looking for dw dt. That's our end goal for this problem. When x equals 6 and when y equals 20. Okay, so those are our values. Okay, so we need to find the derivative, w equals x squared y. So if I'm looking at how this is set up, I see x squared is multiplied with y. These are two distinct terms. I have to not only go through related rates, but there's also product rule involved. So we have to build the derivative first. And once we build the derivative, we should have enough information to insert into our equation to solve for dw dt. Okay, so let's build our derivative using product. F prime g plus fg prime. So f prime, x squared becomes 2x, but every variable has a dx over dt, so we need to attach dx dt. The original g function, no changes. Back to f, x squared, no changes. And then y's derivative is 1 dy dt. Right? We have our derivative. We have everything accounted for. We can insert everything in and solve for dw dt. X gets replaced with 6. dx dt is -1. Y is 20. X is 6. And dy dt is 4. Okay, merge all those values together. We get -240 plus 144. dw dt is -96 units per minute. 22. Let f be a function defined by f of x, on which of the following interval is the graph both decreasing and concave up. So we know that decreasing is going to come from the first derivative sign line, and concavity will come from the second derivative sign line. So why don't we create both sign lines and line everything up and see where we have both these properties lined up within the same interval. Right, so we start off by creating our f prime sign line. So let's make our way to the first derivative. We can go through power rule for each term. Set equal to 0. Factor out of 6. Solve for x. We get 2 and -1. We make our f prime sign line. Populate our sign line. Test each subinterval. So I'll test -2 in for the first interval, 0 in for the second interval, and 3 in for the third interval. Sorry, let's see, I want to put it into the factored form. It's a little bit easier and cleaner to do it that way. Right, so -2 in for x. So -2 minus 2 is negative. -2 plus 1 is negative. Negative times negative is positive. Insert 0 into my derivative. So 0 in for x. 0 minus 2 is negative. 0 plus 1 is positive. Negative times positive is negative. Insert 3. 3 minus 2 times 3 plus 1. Positive makes it positive. So I have increase, decrease, increase, relative max, and relative min. Okay. Now we need to pair this up with concavity, concave up. So we have to make our way to the second derivative. So f double prime. 6x squared becomes 12x, 6x becomes 6, and 12 goes away to 0. Okay. Set our second derivative equal to 0, factor out a 6, find our critical point, and we get 1/2. Right. So 1/2 is our potential point of inflection. We're going to choose points on either side of 1/2, insert into my second derivative. So 0 is to the left of 1/2, 0 in for x, 0 minus 1 is negative. Negative times 6 is a negative, so concave down. Okay. To the right of 1/2, plug in 1 in for x, positive, concave up. So it's easiest to see if we have everything lined up. So I'm going to line up both my derivative functions, sign lines above each other here. So I want I want decreasing and concave up. So I want decreasing and concave up. So decreasing and concave up is going to share within this interval, right? So from -1/2 to 2 is where both properties are showing at the same time. So between 1/2 and 2, my graph is both decreasing and concave up. All right, if f is the function defined above, then f prime of -1 is equal to. So let's go ahead and find f prime. But we see that f prime is split, f of x is split on either side of -1. So let's see what happens with f prime. So f prime, 3x plus 5 becomes 3x. Negative x squared plus 3 becomes -2x. So in order for our slope to exist, if we have different slopes arriving at the same point, then we're going to get a graph that is not going to be this. In -1 in for x, I get +2. and I get a positive 3. So what's kind of happening here is you have a graph that has a slope of positive 3, and all of a sudden, it's going to switch over to a slope of a positive 2, which is still positive, but we see that there's a bit of a sudden change in slope, right? It's not a smooth transition. So the idea is that my slope cannot exist if there's a sharp turn, right? If there's a bit of a corner, because there's not a smooth transition. It's 3, and all of a sudden it just changes to a positive 2. So the slopes on either side of -1 are not the same, resulting in a sharp turn or a sharp point. Therefore, the slope at -1 is considered undefined. All right, 24. Let f be the function defined by what's given. Which of the following is a horizontal asymptote? So a horizontal asymptote is where the numerator, we compare degrees to the numerator and denominator. It's a little bit easier to compare degrees if we don't have those parentheses in the way. So I'm going to FOIL everything out and see if I can get a more clear picture of what's going on. So if I FOIL all this out, the numerator, we get negative 12x squared, plus 15x minus 32x plus 40. And denominator, I get 2x plus 1 times 2x plus 1, which is 4x squared, plus 4x plus 1. We only care about the leading coefficient for the highest degree. So we target our x squared degree. Degrees are the same. So if the degrees are the same, then we know our horizontal asymptote is just the ratio of the coefficients. So negative 12 over 4, which is negative 3. All right, 25. If y is equal to x squared minus 2x and u equals 2x plus 1, then dy over du is equal to. So the way I went about doing this was, well, dy over du means that I want to find the derivative of y with respect to u. So what if I just created an equation where I have y is equal to, and then the right side in terms of u. So I basically wanted to solve for x, find a substitution for x in terms of u, and then that way I have my y equation in terms of u, and I can just find dy over du. So I solve for x here. So 2x plus 1 equals u. 2x equals u minus 1. Divide both sides by 2. X equals u minus 1 over 2. So I made this substitution in for the other equation here. Replace the x with u minus 1. And here I just began to FOIL this out. So I get u minus 1 times u minus 1, which is u squared minus 2u plus 1 all over 4. Minus, I'm able to get the 2's to cancel out. So minus u, distribute the negative through, minus u plus 1. And I split up every fraction, combine like terms if I could, and I just want to get ready to find my derivative. Okay, so here, derivative with respect to my independent variable u, 1/4 u squared becomes 1/2 u, minus 3 halves. 3 halves u becomes just 3 halves, and the 5/4 constant goes away to 0. If I factor a 1/2 out, I get u minus 3. It's still not quite matching my answer choices in terms of x. So I made another substitution here. I know that I want to get my variable back in terms of x. So replaced u with 2x plus 1. So inserted 2x plus 1 in for u. Combine like terms. 1 minus 3 is negative 2. Distribute the 1/2 through. 1/2 times 2 is 1x. 1/2 times negative 2 is negative 1. So I'm left with x minus 1. Answer choice D. (26). We want to find the derivative of a definite integral. This should remind us of second theorem. So second theorem says, take the derivative when the derivative and integral notation are next to each other. We can take a shortcut meaning that we can just jump to the end. So the end, what's going to happen is the upper bound is going to get inserted into the variable of our function, and then we're also going to be able to have to multiply it by the upper bound's derivative. Okay, so we just follow that rule there. Upper bound in for our variable of our function. We get 1 plus x to the 1/2 quantity squared times my upper bound's derivative. So square root of x is really x to the 1/2, and x to the 1/2, we go through power rule, we get 1/2 x to the negative 1/2. Do some cleanup there. We get 1 plus x times 2 root x, and put all that under one fraction. We get 1 over 2 root x, parentheses 1 plus x. Okay, 27, the particle moves on the x-axis so that at any time t, between 0 and 1, its position is given by x of t equals sine of 2 pi t plus 2 pi t. For what value of t is the particle at rest? So particle at rest means my particle is motionless. My particle is motionless when velocity is 0. So we need to first get to velocity. To get to velocity, we need to find the derivative. And to find the derivative, we got to apply the appropriate derivative rule and a little bit of chain rule as well. Right, so sine of u becomes cosine of u times u prime. 2 pi t just becomes 2 pi. Right, linear becomes a constant. We set our velocity equal to 0. Try to separate the terms. I get negative 2 pi is equal to 2 pi cosine of 2 pi t. And do some more cleanup here. Divide both sides by negative 2 pi, or by 2 pi rather. And I'm able to get that left side to be equal to negative 1. So we can ask ourselves, when is cosine of 2 pi t equal to negative 1? And if I want to clean this up a little bit here, I can move that cosine over to the other side. So basically I make it an inverse cosine. Sorry, we make that inverse cosine here. So inverse cosine negative 1 is basically saying, when is cosine equal to negative 1? And cosine is equal to negative 1 when theta, or when t is equal to pi. So we know that inverse cosine of negative 1 is just pi. And now we can just solve for t a lot quicker, a lot easier. Divide both sides by 2 pi. We get t equals pi over 2 pi, which is 1/2. T equals 1/2. Okay, any questions so far? Okay. '28. Shown above is a slope field for which of the following differential equations? So I'd like to gather some information about my slope field here. First is that the whole numbers are kind of split up with every other tick mark. So 1, 2, 3. Okay, 1, 2, 3, 1, 2, 3. So it's a little bit spread out here with these whole numbers. All right. So we want to know which of these slope field actually produces this graph. So I'd like to gather some information here. I'd like to gather, where do I see slope 0? Where do I see slope undefined? And what do I notice about each of the quadrants? So here I see slope 0 occurs when y is equal to 1. So that means if I insert 1 into my derivative, I should automatically get 0. Right? If it doesn't give me 0, then I can remove it. It's not part of my my answer choice. So if I insert y in for 1, this one is okay. But if I insert 1 in for y, I'm not getting a 0, right? So without getting a 0, then I know that my answer choice B is not going to work. So I can remove that option. Second is I look at each of the quadrants here. So anything above y equals 1, I'm getting a positive slope. Anything in the second quadrant where y is to the above 1, I'm also getting a positive slope. Quadrant 3 is all positive slope, and all of quadrant 4 is negative slope. Okay, so I'm just going to choose some order pairs here. What if I chose 1, -1? So 1, -1, and see what happens. If I insert 1, -1, just to kind of test, I know I'm getting a positive number. I should get a positive number in return. So if I plug 1 in for x and -1 in for y, I get -1 times -1 minus 1. So negative times negative is positive. So this one's good. This has the potential to be our answer choice. Let's test the other ones here, C, D, and E. Oh, and also we can also eliminate C because it also fails this test, right? If I insert y in for 1, I get 1 minus x squared, which is not necessarily 0. So B and C are out. D and E is okay with this because if I insert 1 in for 0, I am getting 0. So these are still problems that are choices that are possibilities. But if I insert like an order pair, let's say in the third quadrant, -1, 1, -1, -1. If I insert -1 in for x and -1 in for y, I get negative times a positive, which is negative, and that is obviously not what I see here. So this answer choice is out. If I insert -1, -1 into my last choice, -1 minus 1 is -2. -2 cubed is still negative, and -8 is not displayed here. So I know all the answer choices are not correct except for answer choice A. Okay, so moving on to the calculator active. Now notice that this is a little older test, so the time and number of questions is a little bit different than what it is now. Now I believe it's going to be 45 minutes and 15 questions. And the first part is going to be 30 questions, 60 minutes. All right, so 76 off of the calculator portion. A particle moves along a straight line so that at time t greater than 0, the position of the particle is given by s of t. Velocity given by v of t, and acceleration is given by a of t. Which of the following expressions gives the average velocity? So average velocity, if we're given everything in terms of position, the average velocity is defined as change in position over change in time. So we have s of 2, we have s of 8, s of 8 minus s of 2 over 8 minus 2. And this cleans up to be just answer choice C. All right, 77. We have sine for x squared plus 1 is not f of x, but this is actually the antiderivative of x, of f of x. So we got to keep that in mind. So we're going to build that relationship there. The integral antiderivative of f of x is sine of 1 over x squared plus 1. Okay. So that's a relationship, which means that if I want to find the antiderivative of f of x, then this is already at the antiderivative level. So the integral of f of x, which is really just going to turn into sine of 1 over x squared plus 1, evaluated between 1 and 2. Okay, upper bound first. 1 over 2 squared plus 1, which is sine of 1/5, minus, insert 1 in for x, 1 over 2, 1/2. So sine of 1/5 minus sine of 1/2 is equal to negative 2.81 or negative 0.281. So what we don't want to do is we don't want to say, oh, just replace that in for x and for f of x and say that the integral from 1 to 2 of sine of 1 over x squared plus 1, and then just enter that into the calculator. Okay, so that's not, if it says that sine of 1 over x squared plus 1 is equal to f of x, then we can do that. But it's the antiderivative of f of x, so it's already sitting at the antiderivative level. It's not sitting at the function level. So this is not what we're doing. Okay, 78. The function f is differentiable and increasing for all real numbers x. And the graph of f has exactly 1 point of inflection. Of the following, which could be the graph of f prime, the derivative of f? So we know that we're dealing with a derivative graph, an f prime graph. So if we're looking at the derivative graph, and the graph is always increasing, then if a function is always increasing, then that means the slope is always positive. And if the slope is always positive, then if we're looking at the f prime graph, it should always live above the x-axis. So anything that has any portions below the x-axis is automatically out. So B is out, C is out, D is out, only choosing between A and E. Okay. But we're also told that there's exactly 1 point of inflection, and a point of inflection means only one peak or valley. So here, there's only one peak or valley. There's a valley. Here, there's multiple, right? I see two or one peak and one valley. That's more than this restriction here. So answer choice A. Okay, 79, maybe I'll work this out from the beginning. Okay, a vase has a shape obtained by revolving the curve y equals 2 plus sine x from 0 to 5. So y equals 2 plus sine x, we can enter that into our calculator. Okay, so from 0 to 5, it's going to kind of take on that shape there. From 0 to 5. Between that and the x equals 0 and 5, and also about the x-axis. So here's our shaded region. We're rotating it about the x-axis. So there's no gap between the graph and the x-axis. This is going to be volume using this method. Here's the volume formula. Okay, pi r squared. So radius, big R, is just the distance from the axis of revolution to the curve. Only one radius is needed. Okay, so top minus bottom. Top is the 2 plus sine x. The bottom is 0. So 2 plus sine x minus 0 is just 2 plus sine x. We just insert into our formula from 0 to 5. Right, the rest just goes into our calculator. Okay, math 9. Okay, I already have the 2 plus sine x stored under my y1. 25.501 pi, and that if I multiply the pi through, 25 times pi is 80.115, answer choice E. All right, number 80. Table gives the selected values of function f. The function is twice differentiable. Let me work this out in a separate sheet. Twice differentiable means that's a smooth curve all the way through. And f double prime is always greater than 0. Okay, second derivative is always greater than 0. Which of the following could be the value of f prime of 3? So let's first find out what is the slope at each of these intervals here. So we know that second derivative is going to be involving rate of a rate. Okay, so if I just find the slope here, it kind of gives me a starting point here. So if I do slope between 1 and 3, I did change in y over change in x. And that gives me, in the calculator, it'll give me 0.6. Between 3 and 5, my slope is 5.4 minus 3.6 over 5 minus 3. This gives me 0.9. So the function is twice differentiable. What that means is the rate of change should always be increasing, right? The second derivative means that the rate of change is always increasing. So if it's always increasing, that means if the slope between 1 and 3 is 0.6 and the slope between 3 and 5 is 0.9, then it has to continue in that pattern. And the only value that's between 0.6 and 0.9 and continually increasing, right? Because my rate of change is always going to continue to increase. The only choice is going to be 0.7, right? 0.6 is not going to, it has to be continually increasing. 0.9 is not quite there. 1.2, 1.5 is too large. Only 0.7. Okay, so since the rate of f of x is always increasing, that's what the second derivative is telling us. Rate of change, that's f prime, always increasing, that's f double prime. Then the progression from 0.6 to 0.7 to 0.9 is going to fit that pattern. All right, 81. At time t equals 0 years, the forest preserve has a population of 1,500 deer. If the rate of growth of the population is modeled by R of t, that's rate, what is the population at time t equals 3? So if we know the formula, or if we know how to adapt the formula, it's pretty straightforward. Final population equals initial plus displacement. So we know the initial population is 1,500. We know that the change in population is just the integral from 0 to 3 of R of t. That goes into our calculator, and we get 8641. We start off with 1,500. We're going to gain 8641, and after 3 years, we're going to have a total of 10,141. Right, 82. The figure above shows the graph of f prime. So as soon as I see f, I'm going to start labeling what my graph is doing here. Anything above the x-axis is positive slope. Anything below the x-axis is negative slope. I'm going to plot all my critical points, which is -2 and 2, and 7 as well. And I'm just going to label what I see above, below. Above is positive slope, below is negative slope. From 2 to 7 is still negative slope, still below the x-axis. And then from 7 onward, it's a positive slope. So we see there's a relative max at -2, neither at 2, and the relative min at 7. And also, if we're looking at the derivative graph, we know that the points of inflection is going to come at the peaks and valleys. All right, so the relative max and relative mins of my f prime graph is going to be where the points of inflections are. So I can create a second derivative sign line at -1, at 2, and at 6. Okay. The negative slope on the f prime graph is going to translate to concave down. A positive slope on the derivative graph will translate to concave up. So concave down, concave up, concave down, concave up. There's a change in sign in each of these subintervals. So we have 3 points of inflection. So 3 points of inflection, 1 relative min, 1 relative max. Answer choice A. Okay, let f and g be a continuous function such that the integral from 0 to 6 is 9, integral from 3 to 6 of f of x equals 5, and the integral from 3 to 0 is equal to -7. Okay, what's the value of the integral to 3 of 1/2 f of x minus 3gx? Now, there's nothing outside the large set of parentheses that is impacting these two terms. There's no foiling that needs to occur. There's no ugly radicals that we have to resolve. So really, I can just separate these and treat these like two separate problems. So I'm going to divide and conquer here. I'm going to separate these into individual problems and just handle them individually. So I'll say the integral, I'm also going to pull the coefficients out in front. So this makes it a little bit easier to manage. I can just take one piece at a time here. The integral from 3 of 1/2 f of x, same thing as just 1/2 integral from 0 to 3 of f of x. And then the 3g of x is also being impacted by the integral. So I'll take this one at a time. Now, I just need to figure out what 0 to 3 of f of x is, right? The 1/2, I can just let that tag along to whatever my my replacement will be. Well, I do have some clues about f of x, so let's build from here. We know that a region from 0 to 6 is 9. The region from 3 to 6 is 5. So what we need is the region from 0 to 3. Okay? But if we have the full region, I can split up into my known and unknown. So my large region is 0 to 6. I'm going to split it up into my unknown, 0 to 3, and my known, which is 3 to 6. And 3 to 6 is 5. 0 to 6 is 9. So if I go through and subtract, I can do 9 minus 5, which is 4. So the integral from 0 to 3 must be equal to 4. So I know this portion is 4. 4 times 1/2 is 2. And then the second part, integral of 3 or integral of x dx. We know that this is not pretty similar, but not quite the same order as what we see here. So I'll flip the bounds, make this integral from 0 to 3, which will make it positive 7. So if I want to match these two together, I need to flip the bounds and adjust the signs. So I can replace this with 7, replace the first portion with 4, and keep those coefficients. 1/2 times 2, 3 times 7 is negative 19. 2 minus 21, negative 19. Yeah, so 1/2 times 4 is 2, 3 times 7 is 21. Okay. All right, these next two I think are pretty straightforward. A, B, and C in the figure are bounded by the graph. So they tell us the area is 14, 16, and 50, but anything below definite integral will have to adjust for it to be a negative. Okay, what is the average value? So that's where we got to make sure we are clear about. This is not just the integral here, it's the average value. So we got to take the antiderivative, but we also have to include this 1 over b minus a. So my a and b values are 0 and definite integral from 0 to 8 can be split up into 4 minus 16 plus 50. So take that, multiply by 1/8, use our calculator. 48 over 8 equals 6. 85, particle moves along the axis, so that velocity is given by b of t. What is the total distance? Total distance is just the definite integral of the absolute value of the velocity function. Okay. Okay, make sure we know how to enter this in our calculator. Math 9 will take you to the definite integral from 0 to 2. The absolute bars are held under math number ABS. Alpha y equals will take you to the math print n over d. .927. All right, 86. The 86 says a line L is tangent to the graph of y equals e to the x at the point k e to the x. What is the positive value of k for which the y-intercept is 1/2? Okay, so we know we have to get through, find our, we have a tangent line here, and we have to match that tangent line with that y-intercept of 1/2. And that can help us, if we line everything up, we can solve for k. Let's here. Tangent line equation. We need order pair, we need slope. Slope is going to be e to the k, because we know the derivative for e to the x is just e to the x. And if I plug k into, okay, so let's go through that process, right? My derivative is e to the x times 1. So therefore, my y prime of k must be e to the k. Right? We have our ordered pair, we have our slope. Let's build our point slope form. Okay, solve for y. Mx, distribute this through here. K e to the k plus e to the k. Now, this is in the form of y equals mx plus b. Okay. So my slope is e to the k, which means that my b value is this whole thing here. So if that's my b value, then I can start linking some information up, right? K e to the kx plus e to the k must be equal to 1/2 because my b value is my y-intercept. So our b value is 1/2. And this is a pretty messy problem to solve, so why don't we just make the calculator do the work for us? Why don't we just bring everything over to one side and set equal to 0? Now, we're not going to use k's in the calculator, right? We're going to use x's. Right, so whatever we solve for, whatever that x-intercept is, that's going to be our k value, right? So there's my y-intercept. Let me see if I can zoom in a little bit more. I can do zoom box. And just going to create a box around that region, that x-intercept there. Let's see. Sorry, I need to make some adjustment here. This needs to be written in probably in a better form here. Let me go back here. I should really put that positive term first. E to the kx plus e to the k minus k e to the k. That way, we don't have that minus and plus throwing us off here. This is a better form of my b value. So we should let the b value be e to the k minus ke to the kx. E to the k. Cross this out here. Okay. Let me try again. Okay, so there's my x-intercept. Second trace, option 2, 0. Pick a point to the left of the x-intercept, hit enter. Scroll point on the other side of the x-intercept, hit enter. Enter a third time. Okay, this is basically 1 e to the negative 13. That's just basically 0. Your x-intercept is 0.768. Okay, 87, the differentiable function has the property that f prime is less than or equal to 3. So the slope is less than or equal to 3. And f of 5 equals 6. So which of the following could be true? So we know that the slope is less than or equal to 3. And what we can do is test all the order pairs with this order pair 5, 6. Has a slope that's less than or equal, right? Because it to have a slope less than or equal to 3, if it's going to fulfill this condition of the slope of every order pair between the slope at any point has to be less than that, right? So we pick up all the order pairs. So we'll test 5, 6 with 2, 0. We'll test 5, 6 with 6, 2, 6, negative 2, rather. And we'll pick 5, 6 with 7, 13. Okay, slope between the endpoints. Each of these order pairs here, change in y over change in x is 2. Change in y over change in x is negative 8. Change in y over change in y over change in x is 3.5. So this is the one that's going to stick out. All right, so 2 is less than 3. Negative 8 is less than 3. But 3.5 is not less than 3. 3.5 is not part of our answer choice. That can make this slope less than or equal to 3. So therefore, answer choice C, which will be 1 and 2. Right, the graph of the differentiable function is shown in the figure. Let h defined by h of x, which is the integral of 0 to x of f of t, which of the following correctly orders h of 2, h prime of 2, and h double prime of 2. So let's go ahead and find each of these functions here. So h of x is the integral. So h prime, if we use second theorem, is the derivative of this depth integral, which will wipe it out. Just inserts the upper bound in for x, multiplied by upper bound's derivative. So f of x times 1, which is just f of x. And once we're here, we just shift everything down one derivative. H prime will therefore become f prime. Insert 2 for each of these. So h of 2 is the area of f of t from 0 to 2. This is obviously above the x-axis, so positive value. H prime of 2 is defined as f of 2. So f of 2 is just the x-intercept, which is y value of 0. h double prime of 2 is f prime of 2. F prime of 2 is asking for the slope of the f graph at 2, and the slope is negative. So if we're comparing positive with 0 with negative, then if we want to order from least to greatest, h double prime is going to be the smallest, followed by h prime, and the largest being h of 2. Answer choice E. Right, 89, what is the area of the region enclosed by the graph of e to the x minus 2, sine of x, and x equals 0? Well, let's find what these graphs are. E to the x minus 2, sine of x, x equals 0 is just the y-axis. Okay, there's my e to the x minus 2. And there's my sine. My sine curve is going to be the one that's sitting above. And that enclosed region with x equals 0 as a boundary is going to be this little region there. So identify that region, identify the x-intercept. Sorry, the intersection there. So if I do intersection, I know I'm starting at 0, but I want to know what that intersection is. I do second trace, intersect, option 5. I pick a point that is close to the intersection, hit enter. Pick a point on the other graph that's close to the intersection, hit enter. Hit enter again. That's going to find me the intersection 1.054. So area is just top graph minus bottom graph. Sine x minus parentheses e to the x minus 2. So careful, even if you have everything set up correctly, you want to make sure that you are protecting the bottom function with a set of parentheses. From 0 to 1.054, you make your calculator do this for you. Math 9, interval from 0 to 1.054, sine of x minus parentheses e to the x minus 2. Into the calculator this goes, and you get 0.745. All right, number 90. Particle moves along a line so that the velocity is given by v of t. So I'm going to enter this in. And, but before I graph, I kind of already know where my x is going to be, right? Look at all my values here. It looks like it's kind of hovering between 0 and 2.057. So if I just go from 0 to 3, I can kind of have an idea that I'm not going to be zoomed in too far in or out if I'm just around the edges of my answer choices. And then for Ymin, Ymax, let's just say from -5 to 5, we can always adjust those values later. Okay, so for what value is the speed of the particle increasing? So this is the velocity graph. The speed of the particle is increasing whenever the velocity and acceleration have the same signs. So velocity and acceleration have same signs, meaning that either velocity is positive above the x-axis and acceleration is positive, which means that there's a positive slope, or velocity is negative and acceleration is negative. So acceleration negative would mean velocity having slope. So I highlighted the portions that would be our correct answer. Let me make my graph a little bit better here. If I just adjusted my y value, my window to not go as high, maybe just go up to 3 here. Okay, so the peak there is going to be where there's going to be I want to find a relative max there. It's very gradual here, so I do want to pick points on either side to get to that maximum. So I'll pick a point to the left of where I think my maximum is, hit enter. Scroll over to a point on the other side of my relative max, hit enter. It finds it for me 1.256. And I also need to find the x-intercept. So x-intercept, second trace, 0. Pick a point to the left, hit enter. Pick a point to the right, hit enter. 2.056 or 2.057. Okay, so speed is increasing when velocity and acceleration have the same sign. So either velocity above the x-axis and positive slope, or below the x-axis and negative slope. So between 0.177 and 1.256. Oh, I also need to find this relative. So there's also this relative min hiding there. Minimum. So it's very gradual, right? I can barely see it. So I'm just going to go as close to the x-axis y-axis as I can, hit enter, scroll to the right, where it goes up. There it is, 0.176, 1.177. Okay, I made it more obvious with my graph here, but relative min, relative max, x-intercept, they all have to be involved for us to find our true interval. Okay, let f be a function defined by for all real numbers such that f prime is greater than 0. That just means positive slope. That means between each of these ordered pairs, I should always get a positive slope. Okay. And second, the rate of change of my slope has to be increasing. Okay. The rate of change of my slope has to be increasing. So first, I need all my slopes to be positive. So I just did change in y over change in x for each of my ordered pairs. -1, -2, -3, that's out. I can't do that. I need my slopes to all be positive. So this one is all positive. This one is all positive. This one is negative with a -1, 1, and 3. So this one is out as well. So I'm down to these three options here. Okay. Now, the second statement, f double prime greater than 0 means that my rate of change of slopes is increasing. So here I have a slope of 2, 4, and 16. The rate of change is increasing here from 2 to 4 and 4 to 16. All right, that's an increasing rate of change. 3, 3, and 3, these are all positive, but we see that the slopes they're not increasing. And here, 8, 6, and 2, these are all positive slopes, but we see that these positives are not increasing. F double prime is less than 0. Rate of change, slopes increasing from 2 to 4 to 6, 16. Answer choice B. All right, finally, number 92. The table above gives values of the differentiable function f and g. F prime, the derivative of f, as selected values of x. G and f are inverses of each other. And what's the value of g prime of 4? So I like to start off building my my relationship here. I know that f and g are always going to be reciprocals of each other. So if I have order pair b comma a for a g function, then I must have order pair a comma b for my f function. And then I know that f prime and g prime at their corresponding points will always have reciprocal slopes. Okay, so I'm just going to make my way. I'm going to start here. I'm going to make my way around this chart until I reach my destination. So I'm gathering some information here. I'm going to start at the bottom corner. Okay, I'm looking for g prime of 4. Okay, that's my end goal. Now, this tells me that 4 is the x value of my g function, right? Which means that 4 must be the y value of my f function. So I know that this is okay. So let's work a bit here. F of what will give me 4? F of -2 will give me 4. But it makes sense that g of 4 gives me -2. All right, we see that reciprocal relationship there. Now, if I can find f prime of -2, then we can use these slopes to kind of help each other out. So if I can find f prime of -2, then this slope is going to numerically be directly connected to this number or related to this number. So f prime of -2, so I find f prime. F prime of -2 is +4. So if f prime of -2 is +4, then g prime of 4 must be 1/4. Answer choice D. All right, any last minute questions? Okay, I'm recording this session, so as soon as it's recorded or downloaded, I will upload it onto my website. Okay. All right, best of luck tomorrow, guys. Have a good night.